Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be discussing on chemical families. And our subtopic for the day is alkali metals. So we have been discussing on alkali metals even in our previous lesson. So today we are going to look at some of the physical properties of alkali metals and also get to have a chance to look at some questions. So you look at some physical properties and questions just like I've said. So let's begin. So one of the physical properties of alkali metals, as you can see from the diagram, is the appearance. And this appearance is usually having a metallic cluster. You are able to see it especially from a freshly cut surface, as you can see in the image. When you cut a piece of an alkali metal, you see a metallic luster, a shiny luster, shiny appearance on top of the metal. So this surface, however, tarnishes after some time. This is because it reacts with oxygen in the air and it forms a coat. That's the reason why it does so when it is exposed into the air. And then the next property is the ease of cutting. In the previous property, we have talked about it having a metallic cluster, especially when it is cut. So ease of cutting, they're usually very soft alkali metals. They are very easy to cut. And this softness and ease of cutting increases down the group. The reason why it does so is because alkali metal have giant metallic structures. They're usually held by metallic boards. Later on, you're going to be discussing on how this metallic board happens. So the metallic board is usually due to the attraction of a positively charged nucleus and of one atom and the electron on the outermost energy of another atom. So it's going to be that attraction between the nucleus and the outermost electron of two atoms or more, depending on how many atoms you have. So the force of attraction is stronger in smaller atoms, and then it's weaker in larger atoms. So if you go look at the size of the atom in group 1 elements, down the group you notice there is an increase in the atomic radius. So this directly affects the strength of the metallic bond. So you have said that if the atom is small, it means it will have a strong attraction because the distance of attracting the outermost electron will be shortened. Unlike for larger atoms, for example, potassium, which the distance between the nucleus and the outermost energy level of the electron is very large, so attraction will be not as strong as for the smaller atoms. That's the reason why the metallic bond in small atoms is stronger than the metallic bond in large atoms. And that is the reason why the softness increases down the group because it becomes less strong. So the next thing is melting point and boiling point. So we have talked about metallic bond in the previous property. That is the same thing that is going to be used in comparison of melting point and boiling point. So if you look at the melting point and boiling point, they usually they have relatively weaker metallic bonds. You're going to be comparing them with other groups as well. So the melting point and the boiling point decreases down the group. The reason why it decreases down the group is entirely because of the size of the atom, which increases down the group. So if the size of the atom is increasing down the group, it means the strength of the metallic bond is decreasing. So the bigger the size of the atom, the less strong the metallic bond. So if there's less metallic bond, or weaker metallic bond, it means it will require less heat or less energy to break the metallic bonds. That's the reason why when you compare the melting point of lithium and the melting point of potassium, you notice the melting point of potassium is very low and the melting point of lithium is very high. This is because potassium have very weak metallic bonds, while lithium has very strong metallic bonds. And we have said the reason why this is so because lithium is small in size, the atomic radius is small, potassium, the atomic size is large. So you can see how the size is directly affecting the strength of the bond, which is directly affecting the melting point and boiling point. You'll come into details on this later on also when we get to bonding. So next we'll look at electrical conductivity. So if we take the alkali metals, you notice that they are very good conductors of heat and electricity. The reason why they are good conductors of heat and electricity is because they have delocalized electrons. We mentioned this in our previous lesson. We said that localized electrons are the electrons that are in the outermost shell, and remember we called them the valence electrons. So these delocalized electrons, remember all the electrons are always free to move, but the ones that are in the outermost energy level, they're even freer to move about. So we call them delocalized electrons. So electrical conductivity is similar for all alkali metals. And I want to mention that electrical conductivity is as a result of this delocalized electron. The more delocalized electrons a compound has, an atom has, the more conductivity is going to have. So you notice in alkali metal, you only have one delocalized electron for all of them. So that's why we are saying that the electrical conductivity is similar. So the word similar is coming because they have the same number of delocalized electrons. So if in metals, the electrons in the outermost energy level do not remain in one fixed position, they move randomly through all the metallic structure, and that is why we have said we have called them delocalized. So the next property is ionization energy. So ionization energy, first of all, is the minimum energy or the least energy required to remove an electron from the outermost energy level of an atom in gaseous state. So this minimum or least energy, it needs to be there in your definition. And remember, what are we doing? This is the energy we are requiring to remove an electron. So there's a process of taking an electron away from the outermost energy level of an atom. And remember, when that happens, you know that you form cations, ions that are positively charged. So when it comes to ionization energy, it is always equivalent to the number of valence electrons. So we have first ionization energy, second ionization energy, third ionization energy. It continues and on and on and on depending on the number of electrons you have on the outermost shell. So for group 1, we have the first ionization energy because it's only one electron that is in the outermost shell. So that is the first electron that is going to be removed. So the first ionization energy is the minimum energy required to remove the first electron from the outermost energy level of an atom in gaseous state. So we have defined in the same manner, but in this case, we have used to remove the first. The key word there is the first electron. So we can go on and say there is a second ionization energy, that ionization energy depending on the number of electrons that are being removed from the outermost shell. So when you look at the trend of the first ionization energy of alkali metals, you'll notice it decreases down the group. So the reason why it decreases down the group is because of one reason. Down the group, we know the size of the atom is decreases. It's increasing, sorry. So the size of the atom is increasing. So the force of attraction from the nucleus to the outermost electron is decreasing. So let's show that so that you can be able to see what we mean. Let's take an example of sodium. So sodium has a configuration of 2.8.1. So we have 2 electrons in the inner shell, 8 electrons afterwards, and then on the third shell we have 1 electron. And then we can compare it with potassium. So the configuration is 2.8.8.1. So this is potassium. So we can draw that. So it's going to be potassium with two electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, and 1 electron in the final shell. So if we look at the distance between the nucleus and the outermost shell, the atomic radius of sodium, and if we compare it with the atomic radius of potassium, you'll notice that the atomic radius of potassium is larger and the atomic radius of sodium is smaller. So when we say the effective nuclear charge of the nucleus, it's holding the outermost electron in sodium strongly in comparison to the nucleus that is holding the outermost electron of potassium. So the distance is small. So this nucleus, which is positively charged, is attracting this outermost electron very strongly because it has to make sure it overcomes the first shell, the second shell, up to get to the third shell. If you compare it with potassium, potassium actually has to go through 3 shells in between before it gets to the outermost shell where the electron is. So you can see that distance is very large. So the attraction is very weak. The nuclear attraction is weak in potassium, but in sodium is strong. If you were to compare these two, of course. So if we want to remove this first electron in sodium, we will require to use more energy than if we were to remove this electron in potassium. Because for the potassium, it's not held that strongly by the nucleus, but for the sodium, it has been held very strongly by the nucleus. So that is the reason why, when we go back to the previous slide, we say that's the reason why the ionization energy down the group decreases. You use less energy down the group to remove an electron from the outermost energy level. It is directly related to the size of the atom, which is directly related to the strength of the nuclear attraction. So the next property we are going to look at is just being able to summarize and check the different properties and how they work together. So we said you can see the ease of cutting. Lithium is slightly hard because you can see the size is very small. So the outermost electrons are the strength of the metallic bond is very strong, while you see in sodium and potassium is easy because the strength of the metallic bond is weaker. If you look at the melting point and boiling point, the same case, we said that the melting point and the boiling point decreases down the group because you said the strength of the bond also becomes weaker down the group, so it will require less energy. Same case with when we were talking about ionization energy, we still talked about the size of the atom down the group. So they are both good. They are all conductors of electricity and heat because they have localized electron, and the atomic sizes increase down the group, and the atomic sizes also increase down the group. So let's go to the next session. We'll do a few questions. So the boiling and melting point of alkali metal decreases down the group. Explain. So we said that the melting point and boiling point is determined by bonds and specifically the metallic bond, which is directly related to the size of the atom in this case. So we will say down the group, the atomic radius increases, thus causing formation of weaker bonds, weaker metallic bonds. Hence, less energy or heat will be required to break the bonds down the group. So down the group, the atomic radius increases, which causes weaker metallic bonds to be formed. So you require less heat to break those bonds down the group. The next question is defining ionization energy. So ionization energy is the minimum energy required to remove the outermost energy, the outermost electron from an atom in gaseous state. So you can go ahead and say it's a minimum energy required to remove an electron from the outermost shell of an atom in gaseous state, but the minimum part must be there. The removal of the electron must be there, and it's in gaseous state. So let's do another one. The information in the table below relates to elements in the same group of the periodic table. Study it and answer the questions that follow. So let's look at the table. You can see G1, G2, G3 with the atomic sizes. You can see G1 0.19, G2 is 0.2, and then G3 is 0.15. So when you look at the atomic sizes, we know that this is the largest, then followed by G1, and then the smallest is G3. So if we look at the question is which element has the highest ionization energy, and give a reason. So we said ionization energy is directly related to the size of the atom. So the smaller the atom, the weaker the nuclear attraction to the outermost electron. The bigger the atom, the weaker the nuclear attraction to the outermost electron. So it is harder to remove an electron in a smaller atom, and it is easier to remove an electron in a large atom. So in this case, when we want the highest ionization energy, we will go for the smallest atom. And we said the smallest atom is G3. So our answer will be G3, and we will say it has the smallest atomic size. So if it has the smallest atomic size, it has the highest nuclear attraction to the outermost electron. So a lot of energy will be required to remove the outermost electron. The outermost electron. And that answers the question. So I hope you have been able to understand some of these properties. So in the next session, we are going to continue with the chemical properties of these alkali metals. So see you then.